Welcome to The Explainer. You know that jagged line, right? The one that's always pulsing on a hospital monitor in movies and TV shows? It's basically the symbol for life. But have you ever stopped to think about what it actually is? Well, today, we're going to decode those squiggly lines. And you might be surprised to find out that it all comes back to some really simple physics.
So, yeah, that's the big question for today. How do you take something as biological as your heart beating and turn it into a line on a screen? A line that a doctor can look at and understand what's going on inside you. It's a fascinating story, really. It's all about electricity, direction, and a little bit of genius simplification.
And you're not going to believe where we start. The key to one of the most important tools in all of modern medicine, it actually begins with something you learned to draw as a kid. Yep, an arrow. That simple shape, that's our starting point.
All right, section 1, direction is everything. Let's get into it. Before we can even talk about the heart's electricity, we first got to get our heads around how physicists think. See, for them, it's not always just about how much of something there is. It's often about which way it's going. That direction part is absolutely crucial. So in physics, things are split into two camps. First, you've got what are called scalars. Think of things like your weight or, the temperature outside. They're just numbers, right? They tell you how much. But then you've got vectors. And vectors are different. A vector, like a car's velocity, doesn't just tell you how fast it's going. It also tells you which way it's going. See the difference? How much and which way. And that brings us right back to the arrow. It's the perfect way to visualize a vector. The length of the arrow, that's its magnitude or its strength. And the arrowhead, well, obviously that tells you its direction. It's so simple, but it's an incredibly powerful concept. So what happens when you have more than one of these arrows, these vectors? Well, it's pretty intuitive. If they're pointing the same way, you just add them together. You get a bigger, stronger vector. If they're pointing in opposite directions, they kind of fight it out, and you subtract the smaller one from the bigger one. What if they're at an angle? Well, they combine to form a new vector, pointing somewhere in between. And if you have two vectors that are exactly equal but pointing in opposite directions, poof, they cancel each other out completely. Gone. This whole idea of combining vectors is going to be super important, so keep it in mind. Okay, section 2, the invisible electric field. So we've got our arrows, our vectors, but where do they live? What world are they operating in? The answer is this invisible field of force that's all around us and actually inside us all the time. And that's called an electric field. You can't see it, of course, but it's the area where electrical forces can be felt. It's kind of like, the space around a magnet where you can feel that pull or push? It's the same idea, but for electricity. It's a space just brimming with potential. Now, to get an electric field inside a living thing like us, you need something specific. It's called a dipole. And don't let the name scare you. It's a simple idea. Dipole just means two poles. You've got a positive charge and an equal but opposite negative charge. You can think of it like a tiny little biological battery. And it's what creates this electric field. What's really cool is how a dipole's field is organized. That main vector we talked about, it always points from the negative end to the positive end. And if you slice it right down the middle, perfectly in between the two charges, you find this line where there's no charge at all. It's called the zero potential line, and it acts as a perfect dividing line between the positive and negative zones. It's a really neat, orderly system. All right, section 3, the heart's electrical signature. So we've talked about vectors, and we've talked about dipoles. Now it's time to connect the dots. Let's take these physics concepts and see how they apply inside the human body, specifically to create the heart's unique electrical fingerprint. But wait a second. A simple little dipole, what does that have to do with the human heart? I mean, the heart is this incredibly complex muscle, right? With all these complicated electrical waves flowing through it every second. So how on earth can we model that with just one simple little positive and negative charge? Well, the answer comes from a moment of pure genius. A guy named Willem Einthoven, one of the pioneers in this field, came up with a wild idea. He said, look, what if we just simplify? What if we pretend that all that complex electrical activity in the heart What if we treat it as if it's all coming from one single dipole right in the middle of the chest? And this model was a total game changer. Einthoven's big idea was to treat the heart as a single point source of electricity. Now, to make the math work, he had to make an assumption that the whole body conducts electricity perfectly evenly. We know now that's not quite true. Different tissues have different resistance, and of course the heart's electric field is changing all the time as the muscle pumps, so later on, science had to make some corrections. But Einthoven's fundamental idea that you can model the heart's overall activity with one changing vector, that was brilliant. It's still the foundation of how ECGs work today.
Okay, section 4, reading the heart's story. So we've got this amazing model where the heart is basically writing a story in the language of electricity, moment by moment. The big question is, how do we read that story? How do we actually capture that vector as it changes and moves?
It's actually a pretty simple three-step process. First, you place electrodes on the skin. You can think of them as little antennas, just listening in. Second, those antennas get hooked up to a machine called a galvanometer. That's the guts of the ECG machine. And third, that machine does one thing and one thing only. It measures the difference in electrical energy between those electrodes. It's just listening to the electrical story the heart is telling. And here's the final piece of the puzzle. It's so elegant. The machine is set up so that when the positive end of that heart vector swings towards an electrode, the line on the screen goes up. And when the negative end of the vector swings towards it, the line goes down. So an upward squiggle means the positive charge is pointing at you. A downward squiggle means the negative charge is. It's that direct. So when you see that iconic, jagged line on the monitor, what you're really looking at is a graph. It's a picture of the heart's main electrical vector, twisting and changing in strength and direction with every single beat, all drawn from the point of view of the electrodes on the skin. It's literally a drawing of the physics that are happening inside your chest. So the heart story, it's written in vectors. By taking something incredibly complex and simplifying it down to a single arrow, we unlocked a whole new way to look at health and disease. And it really makes you wonder, doesn't it? What other secrets are our bodies telling us right now? Just waiting. Waiting for someone to find the right physics, the right model, to finally translate them into a language we can all understand.